In this part of Chapter 4, we're going to be focusing on the cycloalkanes. So we're going to look at cyclic alkanes, and what we are talking about, since they are alkanes, they contain all carbon-carbon single bonds, but they're going to be cyclic, so they're going to have one or more rings. But what we're going to be first talking about are the ones that just have a single ring. And so, for example, cyclopropane would have 3 carbons and would be in the cyclic shape. And we can use heats of combustion to help us compare the relative stabilities of each of these molecules. And you can hopefully see that they're not the true heat of combustion of the individual compound, but rather they have taken the heat of combustion and divided it by the number of CH2 groups so that you can make a comparison. Because the heat of combustion is going to go up based on the total number of carbons. And so we're just going to focus on the per CH2 group and make some comparisons there. And I like to compare these to an unbranched alkane to see if there's any difference in stability. And then sometimes we'll often look at the change in that combustion, which can give us an indication of strain. And so if we look at that from that difference, we could see that a cyclohexane has really no difference from an unbranched. And we can also hopefully see that we have an increase in the combustion or strain with the very small molecules like the cyclopropane. And so this difference in energy is referred to as ring strain. It's an extra strain associated with trying to make some of these compounds cyclic. And it's composed of 2 different components, one being angle strain, because again, we are dealing with sp3 hybridized carbons, and you would expect their bond angle would be 109.5. However, in this particular case, we're going to have angle strain because we're going to either be less than or greater than that. And what this can lead to is insufficient overlap of the sigma bonds. Torsional strain is going to be an eclipsing strain, as we're going to see, much like we saw in part 2 of this chapter, that we will have some eclipsing interactions. Cyclopropane, as we said, is 44 kilojoules per mole less stable than a cyclohexane per CH2 group. And it's going to be highly strained for both of those things that we talked about a moment ago. So the angle strain, the bond angle is 60 degrees. And this, of course, is significantly less than the 109 that we would have normally expected for an sp3 hybridized carbon. So the carbons are still believed to be sp3 hybridized. However, they are not at that expected bond angle. And so we can see that what also happens in doing that is that it's going to try not even to maintain that true 60, because here's a true 60 degrees. You're going to start having kind of this going back out to trying to be closer to that 109. And what's going to happen is that there's going to be this insufficient sigma bond overlap then that is observed. The other thing we can do with cyclic compounds is we can try to look down a bond, much like we did with our straight chain alkanes, or even our branched but non-cyclic alkanes. And if you look down a carbon, what you're going to see is that if it is truly planar like you would expect, there would be a total eclipsing of each of those things. So we would have these eclipsing interactions, which is going to increase the energy or the torsional strain. Cyclobutane is a little bit less stable than cyclohexane, but not as bad as the cyclopropane was. Now, you would normally have predicted that the cyclobutane would be planar possibly, if you were to kind of think about it and draw it, but it really is not going to be planar. And so it's going to exist more in a puckered geometry, as we can see in the image here. And the reason for that is to avoid being fully eclipsed. And so if it was completely planar, it would be fully eclipsed. Now, the interesting thing is the puckering, of course, reduces the bond angles. Normally, you would predict in a square that those would be 90 degrees, but actually it is going to reduce it slightly to pucker it, but that advantage to puckering it and avoiding the eclipsing is more advantageous than the shift from a 90 to an 88 degree bond angle. Cyclopentane is relatively stable. Its angles are close to the optimal. They're about 108 degrees. And again, it is going to be puckered to avoid some of the torsional strain. And it's often referred to as a puckered envelope. And sometimes the reason why not on the way that it's drawn there, it's a little hard to see, but if I were to draw it this way, and I've kind of exaggerated the envelope flap here, it would not be quite that exaggerated, but just to kind of show you, that it's kind of like an envelope flap there. The reason why cyclohexane is considered to have zero ring strain is because it takes on a non-planar conformation, which is referred to as a chair. And so the bond angles are exactly 109.5. And if we were to look at the conformations, the stagger conformations, so our little eyeball is going to be such that it's looking down these bonds. So I'm going to call this carbon 1, 2, 3, 4, 5, 6 to help you. So this front carbon would be carbon 1. Here's where carbon 2 would be. Here's carbon 3. This back carbon is carbon 4, 5, and 6. So hopefully you can hopefully see how that is arranged. And hopefully you recognize that this is a staggered conformation, which would be lower in energy. There are alternative conformers. Remember that conformers are just found from rotation of sigma bonds. The boat is one of the alternative conformers of the chair. This is less stable. There is no angle strain, so the bonds are still 109.5, but there is torsional strain because you are going to have eclipsing bonds, and we can draw the Newman projections to see that. So again, I'm going to kind of call this 1, 2, 3 in terms of my carbons. And so if our eyes are over here looking down on carbon 1 and 3 to 4 and 6, as we're sort of looking down, we can see that carbon 3 has kind of a, so here's carbon 3, here's our hydrogen and our hydrogen. This is going to carbon 2, and then here's carbon 1 with the hydrogens, and then we would have our back carbons. And hopefully if you kind of look then, there's the eclipsing, and carbon 5 also eclipses. And so that is where you can hopefully see the torsional strain from that eclipsing. The other issue is that there are these top hydrogens here that are kind of pointing to each other, and one could kind of treat this, if you're looking at this like a boat, that they sometimes refer to those as the flagpoles, and there's going to be some interaction between those flagpoles as well, which is going to be a form of steric strain. Just like we did the conformational analysis of alkanes, we can do a conformational analysis of cycloalkanes, and we would start with the lowest energy state being the chair. And what's going to happen is, and this may be essential for you to get out a model to try to build the model and look at this, but if you were to, so in a sense, we're going to call this our headrest for the chair, and this is our footrest. And then you sort of have that middle part that I haven't highlighted. That's sort of, where one would rest. So if I were to bring up the footrest partially, not all the way up, but kind of partially so that it's now in the plane with that bottom part. So all of these are sort of, the part that I've done in the green is in the plane. This is a lot higher in energy because you are actually having a bond angle here that is greater than 109.5 degrees in this portion that's kind of been made planar. So you're going to increase the angle strain there. You also are going to start eclipsing some bonds, and so again we're going to have some torsional strain as well. So then we're going to continue to bring the top part up so that now it is could be going into the boat. However, there's a slightly lower conformation in which you twist the boat, and what this does is this alleviates some of the torsional strain. And then we have a boat, then another twist boat, then we start bringing the blue side down so that now we have our half chair, and then finally the opposite chair, where now, our headrest is now down as a footrest, and what was our footrest is now up as a headrest. It's really critical that you learn to draw the chairs properly, and so your textbook goes through kind of a nice way to show how you do these sets of parallel lines when you're drawing them. Then it's also important that we pay attention to where the atoms are that are attached to them. And there's two types of hydrogens. Ones that are referred to as axial, so if we were to kind of think about like, the Earth, these are the ones that are on the axis, and so they are pointing straight up and down, and they alternate. And what I usually like to do and tell students to do is start on the headrest, and notice it goes up on the headrest, and so then the next carbon it goes down, then the next carbon it goes up, then the next carbon it goes down, next carbon is up, and next carbon is down. And so hopefully that will help you, and it is not this way. So, that's why I say start on the headrest and always make it up, or if you'd rather, you could start on the footrest and always make that down. The other type of hydrogens are going to be those that are in the equatorial position. So almost like the equator on the Earth, because they're going to kind of be more in the middle of rather than going up and down, they're going to kind of be pointing out. And they're going to be parallel to those lines that you drew at the beginning. And if we were to look at a chair below, so I'm going to go ahead and draw a chair and kind of help you see this. So again, we're going to start with the axials in red. So we'll go up on the footrest. Each of these would be down, up with that. So there's where our axials are. Now our equatorials. So if you notice now I have a red that was up, my equatorial is going to be down, kind of pointing out. Here my equatorial will be going up, and the same thing with that one. So they're pointing up. Here it's pointing down, down, up, down. And so hopefully you can get used to drawing those that way. So we're going to do a chair flip for each of these molecules. So the first thing, of course, that you need to do is draw your chair, and I'm going to again try to do, so I'm going to do my axials blue in this particular case. And then we'll do our equatorials in green. Now, as I mentioned when we were doing the conformational analysis, what's going to happen when you do a chair flip, so this is carbon 1 here, it is going to become it's right now a footrest, it's going to become a headrest. So here's still carbon 1, 2, 3, 4, 5, 6. So hopefully you can see that the carbons have corresponded. So like carbon 4 was the headrest, now it's a footrest. Now this time I'm going to keep the same colors because I want to show you something. So the blue hydrogens that were axial, they're still going to be staying pointing down, but they are now going to, or up depending, so on carbon 1 it was down, but it's now going to have converted from an axial, to an equatorial. And the same thing is going to happen with each of these. And notice that they are still pointing in the direction that they were on the original structure. You know, they've just changed their conformation. And now what was our equatorial are now our axial, alternating again, pointing up and down. All right, so on the previous slide, we looked at the chair flipping for a individual cyclohexane molecule not substituted, and you saw how there were the differences between the equatorial and the axial hydrogens. Now we can look at if there is a substituent. So we could have the substituent in the equatorial up position, pay attention that that bond is going up, versus here in which it is now in the axial, and it is still also in the up position after it did the chair flip. And if we look at the Newman projections, hopefully you can see, and they're just showing you kind of the arrows are indicating the chair flip, but hopefully you can see that in the equatorial, the group is kind of out to the outside of the molecule and less sterics. So there's less sterics involved in this, whereas in the axial, we actually have a gauche interaction between that other carbon, because remember this is a CH2 group in here, and so there's going to be a gauche interaction with that, which is going to increase its energy, making it less stable or higher in energy. And so looking at a methyl disubstituted, again with the group here now, the axial is on the left and the equatorial is on the right, you can see that at room temperature, 95% of the molecules are going to have that methyl group in the lower energy state where it is equatorial. And if we start looking at this, again, this is just looking at a gauche interaction, remember, in a alkane, just a non-cyclic alkane, versus now here we have what we call the 1,3 diaxial interactions. And you can see that again here, where we are getting that van der Waals overlap in the, because this would be carbon 1, let's say carbon 3, so you have a 1,3, or it could have gone the other way, diaxial, because they're both in the axial position, and it raises the energy of that species. When you have the substituent in the equatorial position and you're looking at kind of relative to that CH2 group, it is in an anti-conformation and therefore is the lower energy state. And depending upon the size of the group, the larger group sizes will cause more sterics in that 1-3 equilibrium. And so you can see as the group increases in size, the amount of steric hindrance increases. So when we have di-substituted or two substituents, we need to pay attention to how their position is, whether they are up and down in the ring, and then to actually keep that geometry within the chair. So in this particular case, we have an example of a trans geometry because the chlorine is up and the methyl is down, so they are on opposite sides of the ring or opposite faces of the ring, and therefore with the opposite, that's where we get the term trans for that. And then here's an example where our chlorine is up and it's axial, and our methyl is down and axial, and so they are opposite of each other. The other possible chair, if you do the chair flip, the chlorine is still up, but it is now equatorial, and the methyl is still down, but it is equatorial. And so which of these chairs would be more stable? We know that putting a substituent in the equatorial position would make it more stable. Having both of them would definitely increase its stability, so this would be the more stable chair. So this is now another type of stereoisomerization. These are not structural isomers because there's no difference in connectivity. So they are not considered structural or constitutional isomers. They are what we call stereoisomers. So there's no difference in their connectivity. There's just a difference in the orientation of the groups in space. So they have the same connectivity, different stereo geometries. So when we name them, if they're disubstituted, we'll use either the prefix cis or trans. Cis is when the two groups are on the same side of the ring. When the two groups are on the opposite sides of the ring, we refer to them as trans. And so your naming would be cis, and if you're typing this, these prefixes would be in italics. So cis 1,2-dimethyl cyclohexane versus trans 1,2-dimethyl cyclohexane. So let's do another example here where we have a cis 1-ethyl 3-methyl cyclohexane, and we want to decide which is more stable. So because they're cis, they're both going to be on the same side. So I'm going to start with my carbon 1 here, and I'll put my ethyl in the axial direction. There would be a hydrogen here. If you would prefer, you could instead, write your ethyl as a CH2CH3 group. And so that's carbon 1. You could go either way around the ring to get to carbon 3. I'm just going to make this carbon 3 here. Since they're cis, they're on the same side, so my methyl must be up, or I can draw it up like that. Then if I do a chair flip, I am going to then still keep the groups up, but now it's now the footrest instead of the headrest, and my methyl would be here. And here both groups are axial. Here both are equatorial, and so obviously with both of them being equatorial, this is going to be the more stable conformation. And it would be more stable by about 15.6 kilojoules per mole, because if you go back to the table and add them up, you would have about an energy savings of 15.6 kilojoules per mole. What if we were to do the trans 1-ethyl 3-methyl cyclohexane? So I'm going to put my ethyl up, but now my methyl is going to be down, and it's going to be down in the equatorial position, because recall that, of course, the axial position would be the hydrogen. And now if I chair flip this, my ethyl is still going to be up. My methyl is still going to be down. And the structure would look like this. Now, if we go back to our table, recall that an ethyl axial gives about a stereo hindrance of 8 kilojoules per mole, and a methyl is 7.6 kilojoules per mole. And so that's why, of course, when we had them both axial, that's where we get the 15.6 from. So in this particular case, then, this one with the methyl is going to be slightly more stable, because by only 0.4 kilojoules per mole. Because that's the energy savings by putting the methyl or the smaller group axial versus the other equatorial. And of course, we know then that the most stable of all of those chairs for a 1-ethyl-3-methyl cyclohexane would be the cis, in which both of them are equatorial. Polycyclic systems will often exist, and it really just depends upon which rings are there, how they will be present, but we typically would know that a trans situation would be more stable, because notice that it puts these groups in a more linear conformation, and there wouldn't be as much sterics from a cis conformation. And we'll see that in diamonds, where you'll have multiple chairs in those trans geometries fused together. And then finally, you will often see some polycyclic structures with sterols, and they will often have a somewhat linear structure in their chairs that are involved in the rings there.